Welcome to Spring LIB.
For this question, we're going to use the example 32-2, right? Since we are dealing with a cyclotron, from the kinetic energy, we want kinetic energy to be 12 MeV, right? For the deuteron to be accelerated, and from here we should be able to get the magnetic field by using the kinetic energy equation, right? K equals to QBr square divided by 2m. We have all the necessary values, right, such as the radius, the charge, and the mass of our particle. So we should be able to get the magnetic field. So just rearranging the equation over here, then we should get V to be equals to 2m times Ke over Qr, right, square root at the numerator. So we just have to substitute all these values in. So for the mass of our deuteron is approximately 2.014 U atomic mass units. So we multiply it by the conversion factor from atomic mass units to kilograms. So this will be in terms of kilograms. The kinetic energy is given as MeV, so we have to convert this into joules. So this is the conversion factor from MeV to joules. And then we have the charge. And the charge for our deuteron is just 1 1 elementary charge, so that's just 1.6 times 10 to the power minus 19 coulombs. The radius is given as 1 meters. Right, and so substituting everything, we should get 0.71 Teslas. Now next, to find the frequency, we use equation F goes to QB over 2 pi m, right? Since we already found our magnetic field. So what we have to do, we just substitute in the various values. So the charge is the same, right? Same elementary charge, 1 elementary charge. The magnetic field from before, pi times the mass we should get our frequency to be 5.4 times 10 to the power 6 Hertz, right, or 5.4 megahertz. Now we are given that the potential difference is 22 kilovolts, right, between the D's, and we want to find how many revolutions the particles will make. Now we know that the D's are situated as such, and so for each revolution, the particle will actually pass through the potential difference twice, right? So what it means is it will be accelerated twice for every revolution, and we know the amount of energy that is gained, right, by QV, right? So the energy gain per revolution will be equals to 2 times of QV, because there is 2 acceleration positions, and the amount energy gained per acceleration will be equals to q times the potential difference. So the number of revolutions that we will need, we just take the energy, which is 12 times 10 power 6 electron volts, right, 12 MeV, divided by the energy gain per revolution, which is 2 times of the potential difference times the charge, which in our case is just E, right? So this will be 22 times 10 power 3 EV. We should get our answer to be about 273 revolutions, which is approximately 270. To find what is the time needed to go from start to exit, we will need to find using the frequency, right? What is the total time that is required? So the frequency that we're given is, which we have found actually, is over here. This tells us how fast the deuteron will be undergoing the revolution, right? So the time needed for the entire acceleration process, we just take the number of revolutions divided by the frequency. So this is just 273 divided by 5.4 times 10 to the power 6. Should get 5.1 times 10 to the power minus 5 seconds. So this is the time required to accelerate the protons, sorry, the deuterons from start to finish. And to estimate its traveling distance, we're going to use the radius and the circumference basically to find the circumference of our cyclotron. But take note that when the deuteron starts to accelerate, it starts from a very at the center, and it starts off as a small circle before going out into the larger circle, right? So it is not correct if you were to just use the entire circumference as the distance, right, traveled. So what we're going to do is we're going to estimate that on average the circumference is going to be half the radius, so at the middle, right, in between the maximum radius, right, so halfway between the center to the maximum radius. So that will be just total distance will be equals to pi r. This is the circumference, right? But we're gonna estimate by dividing the radius by half, multiply that by the number of revolutions, which is 273 revolutions. And so the answer that we get would be 160 meters.